Hi friends, welcome to Kumar Foundation classes. Today we'll understand about force, but before learning force we need to understand mass. Because whenever we apply force on any body, the effect of that force is also dependent on the mass of that body. So let's understand mass first. Mass of any body is the total quantity of substance or matter present in that body. How do we measure mass of any body? Definitely by beam balance or level balance. So for example, whenever we go to buy any item from the shopkeeper, for example, in this case, potato, shopkeeper use level balance to measure the mass, right? So one side they keep one object of known mass, that is in this case 1 kg, and the other side they keep on putting potatoes till the label is not balanced. Once the label is balanced, we understand the mass of potatoes is equal to the mass of object that we kept other side, right? So that's the way we measure the mass of any item. So let's understand about the unit of measurement of the mass. So SI unit of mass is kilogram, and the CGS unit of mass is gram, that we represent in kilogram and gram. So we already know that 1 kilogram is equal to 1000 gram. We will understand more about comparison of mass of two different body. In here I have taken example of silver and gold. I have taken both silver and gold of the same volume, that is 1 cubic centimeter, both silver as well as 1 cubic centimeter of gold. But when we see the mass, measure the mass of these two objects of the same volume, here 1 cubic centimeter, the mass of silver is 10.49 gram, whereas the mass of gold is 19.32 gram. So what we see here, even in the first example where we used iron object of known mass of 1 kg and potato 1 kg, both the example we see that if the volume is same, then the mass is not necessarily same, because even the volume is same, the quantity of matter present in those two different bodies are different. That depends, molecules, which molecule made of which molecules, intermolecular space, properties of that matter. So the quantity of matter is different in two different objects, even the volume are same, right? So two different objects may not have the same mass, even they have same volume. Let's go to understand force now. So force is basically a push or pull effect on any object which cause the change of state of motion or change in the shape of that object, right? So we will understand more about the effect of force. See, here first example I have taken is change of shape of the object, right? So here we see that there's a sponge, and initially basically it is in a cuboid shape, but when we squeeze it, push from outside, the shape of the sponge has changed and it is not in the cuboid form. So this is first effect uh, of the force. The second effect of the force is change of state of motion. So here in this picture, if you see, there's a golf ball which is in the rest state of rest. So state of motion is rest, and when we hit by a stick, then the ball start moving, right? So the state of motion has changed from its rest state to the moving state, right? So we see that whenever we apply force, there's a change in state of motion. Let's take the another example, which is change the direction of the motion. So here in this example, this man is playing tennis, and when a tennis ball coming from from this direction, like in this direction, but when this person hit the ball, it it actually go back in this direction. So the initial direction was, I mean, from our side it is left, and then it is going on the right side. So we see that the direction of motion had changed when we apply force. We applied force on that ball, right? Let's go to understand the type of forces, right? So basically there are two type of forces. First is contact force. So we understand, right, whenever we apply force and there is a need of to contact the body to apply the force, then that force is called contact force. I'll give you two examples like muscular force and friction force. So here if we see muscular force, this person is pushing this block, and to push this block he has to touch or make the contact with the block, right? So here this force is a contact force. That's why I called muscular force is a contact force. The other example, friction. Here, if two bodies slides on each other, then there is a friction to oppose the motion of both the bodies. But when they slide on each other, there is a contact between these two forces. So when friction has arises, when there is a slide, there is a contact between these two bodies, and that's the reason friction force is also a contact force. So we can guess the other type of force, which is non-contact force, right? So non-contact force, when to apply force, there's no need to contact the body. If there's no contact between two bodies and they are applying force on one on another or on each other, then that force is called non-contact force. Let's take some example. Here we see gravitational force is non-contact force. So we know that two massive body attract each other, but they don't need to be in contact to attract each other, right? For example, on Earth, like this is Earth and there's a ball on. We are just leaving a ball on at some height. Ball is dropping towards the Earth's surface. Why? Because Earth is applying a gravitational force towards its center of Earth, and that's the reason the ball is falling on the Earth. But to apply the force on the ball, there's no need to contact, and that's the reason gravitational force is non-contact force. Now there's another example is magnetic force. So we also know that, right, there's a magnet, and if we keep some iron piece at some distance, that magnet attract that iron piece towards the magnet, right, towards itself. So to what magnet is doing, that is applying a magnetic force towards itself. But to apply the force, magnet does not need to touch the iron piece, and that's the reason magnetic force is also a non-contact force. Similarly, electrostatic force, we know that two opposite charges attract each other, and same charges, if there's the same charges, they repel each other, right? But to apply these forces, like if the opposite charges, there's attraction force. So even to apply the force of attraction, they don't need to be in touch, right? Even for the repel also, they don't need to be in touch. But even they are at some distance, this electrostatic force is getting applied. So even electrostatic force is also of non-contact type. Now let's understand how do we measure force. Basically, force is getting measured in vector quantity, right? So there's two type of quantity that we know. One is vector quantity, another is scalar quantity, right? So scalar quantity when we to measure the scalar quantity, we need to only measure magnitude, right? We don't need to measure direction or anything else. Once we measure magnitude, for the scalar quantity, that is sufficient. For vector quantity, we need to measure both magnitude as well as direction, right? So here we say that force we measure in a vector quantity. So what did that mean? For example, here in muscular force again, if that person is applying force on this block, if you are saying, for example, if he is applying 10 Newton force, that is not sufficient information. We need to know that he is applying force in which direction. Then only we will understand, okay, if that person is applying force on the block would move in which direction if he is applying 10 Newton force, right? So when we talk about force, we need to tell both of the things, the quantity of force, how much he is applying, and then direction of the force in which he is applying, right? So force is a vector quantity. Now we will understand about unit of measuring force, right? So unit of force is, the SI unit of force is Newton. What is 1 Newton? So 1 Newton is basically a quantity of force which which can be applied on 1 kg of any body, and which gives 1 meter per second square acceleration to that body. Let's understand properly. There's a body, for example, this is one body, and one force is getting applied on this body, and this body is of 1 kg mass, right? And if the force has been applied, and if the acceleration is this body is getting 1 meter per second square, then the quantity of that force is called 1 Newton. So let's calculate 1 Newton. 1 Newton is what? 1 kg into 1 meter per second square. So basically we know that F is equal to mass into acceleration, right? We will study in detail in our future topic from where this relation comes, but force is equal to mass into acceleration. Mass is here 1 kg and the acceleration in 1 meter per second square, and which is 1 kg meter per second square. So we see that this is the force needed to give 1 meter per second square acceleration to a body of mass 1 kg, and the quantity of this force is called 1 Newton. That's what we have presented here. 1 Newton is equal to 1 kg into 1 meter per second square is equal to 1 kg meter per second square. So clear? 1 Newton is 1 kg meter per second square. Let's understand the dyne, the CGS unit of measuring force, right? So it's easy. Dyne, if we take mass and acceleration both in CGS unit, the quantity of force will be given is dyne. So 1 dyne is equal to, here I have replaced 1 kilogram with gram in CGS unit, and then we have replaced 1 centimeter meter per second square to 1 centimeter per second square. Then the total force is 1 gram centimeter per second square, and that is called 1 dyne. So 1 dyne is equal to 1 gram centimeter per second square. The relation between Newton and dyne is, like we will calculate here, it is 1 Newton is equal to, as from here, 1 kg into 1 meter per second square. Let's convert that kg and meter per second square into CGS unit. This is 1000 gram, then 100 centimeter per second square, and it is 1 lakh gram centimeter per second square. That is 10 to the power 5. And gram centimeter per second square is nothing but dyne. So 1 Newton is equal to 10 to the power 5 dyne. I hope it is clear. Now let's understand unit of gravitational force, right? The question would come in mind that if we have already understood about the unit of force, why there is a separate unit of gravitational force, right? So in unit of force, what we talk about when 1 kg of mass is getting 1 meter per second square, that force is required to give the acceleration of 1 meter per second square to that body is called 1 Newton. But in gravitational force, what is the acceleration Earth is giving to any body is 9.8 meter per second square. So we will talk about the force required to give 9.8 meter per second square acceleration to any body of mass 1 kg, right? So the force required to give the acceleration of 9.8 meter per second square to a body of 1 kg is called the unit of that force, and we call it as 1 kilogram force, right? 1 kilogram force. So SI unit of gravitational force is kgf, which is kilogram force. This is kgf. So 1 kgf is 9.8 Newton, right? I have already explained it. So we can calculate 1 kgf is what? 1 kilogram. The mass of that body is 1 kilogram, and the acceleration which arises is 9.8 meter per second square. So total force is required 9.8 kilogram meter per second square, which is nothing but 9.8 Newton. So 1 kgf is 9.8 Newton. Clear? So we'll understand in CGS unit also. So CGS unit, the unit is called gram force, which is GF. So gram force, that is GF, and 1 GF is equal to 980 dyne. So let's calculate how much dyne is coming in 1 GF. So 1 GF in 1 GF, this is 1 gram, the mass of the body in CGS unit, but the acceleration what it getting is in centimeter per second square is 980 centimeter per second square. So total 980 gram centimeter per second square, and the total dyne we can say it is 980 dyne. So 1 gram force is equal to 980 dyne, right? So to give a unit for gravitational force, in SI unit it is kgf, and in CGS unit it is gf. We can also measure in definitely Newton and dyne, but the unit of gravitational force we can say kgf and gf. Now let us understand about weight. So what is weight, right? So basically weight is nothing but the gravitational force. For example, on Earth, if we are talking, Earth is applying some gravitational force on any body, then that gravitational force getting applied on that body is called the weight of that body, right? So if you here in this example, if you see this is Earth and a man is standing on the Earth whose mass, for example, let's consider m, and there's weight is basically there's a weight, then the weight of this person will be the gravitational force Earth is applying on this person, right? It's a gravitational force. So we can calculate how much gravitational force Earth is applying on this man, then that force will be nothing but the weight of that person, right? So let's calculate how we can calculate. It is mathematically W, weight is equal to mass into gravitational acceleration. The relation holds good that we know that F is equal to ma, that is mass into acceleration. So force is here the force is W and mass is definitely m, and but the acceleration here is gravitational acceleration. So weight is nothing it mass into gravitational acceleration, right? So this is the relation. I have already explained here. W is weight, m is mass, and g is gravitational due to gravity, right? And weight depends on gravity, as we already told that weight depends on gravity. But gravity on different planets are different, right? So if you see that it changes, the weight it changes from place to place, right? For example, I have taken less on moon and then then earth, right? So right, same person if he is moving to moon, right, then that person, the weight of this person will not same, it will change. So we know that roughly the gravity on moon is around 1/6 of the gravity of earth. The weight of this person will also be about 1/6 of the weight, which is weight on the earth, right? So right, if we say that weight on moon is equal to nothing but weight on earth by 6 of this person, right? So weight on different planet of any body is different based on their gravity, but the mass is same. Mass is what? Mass is the quantity of substance and matter present in this body, right? Which is not going to change whenever that person is changing the place. So if the place of the body is getting changed, right? If the body is on earth or moon or any other planet, the mass of that body is not changing because the substance or quantity of substance matters doesn't change, right? I think we are clear about it. So let's take some example to calculate the weight. Here the question is mass of the body is 10 kg, right? So what is the weight? The gravitational acceleration has given 9.8 meter per second square. So we know that weight is equal to mass into gravitational acceleration. So here mass is what? 10 kg, and g is already given 9.8 meter per second square, right? So the total amount is 98 kg meter per second square, and so it is 98, and this is what? Newton, right? So it is 98 Newton. So weight of that person is 98 Newton, right? Let's take another example. Here we are comparing the body present on Earth and Moon. So let's calculate it. Let's take and draw a picture to understand better. Let us say this is Earth, this is Moon, right? And there's a body, same body here also on the Moon. And so on the Moon, okay, the mass is 80 kg, right? On both the places, here also mass is 80 kg, and the gravity here basically GE. On Earth, the gravitational acceleration 9.8 meter per second, so it is 9.8 meter per second square. Here G is equal to, it is given 1.7 meter per second square, right? So let's calculate. Here it will be WE and it will be WM. So let's calculate WE first. WE is equal to, again, mass into gravitational acceleration on Earth, which is equal to 80 into 9.8 meter per second square. So 80 into 9.8 is 784 kg. So it is kg meter per second square, and so it is 784 Newton. We can directly write, 80 into 9.8 Newton instead of putting kg or meter per second square and meter per second square, right? We know that it will come kg meter per second square, so we can directly write Newton. We will calculate in the same way for Moon. So for Moon, Wm is equal to mass into gravitational acceleration on Moon. So it is, it again, mass is same, but the gravitational acceleration is 1.7 and meter per second square, but we can write Newton directly, and so we will calculate 80 into 1.7 is nothing but 136 Newton. So what is the difference? The difference is WE minus WM, which is 784 minus 136 is equal to 648 Newton. So the weight of that body on Earth is 648 Newton higher than the weight of that body on the Moon, right? So I hope it is clear about understanding of force, mass and weight. If you have any question, please put it in the comment box so that I can answer those questions. And thank you for joining the class, and let's connect again in another topic. Thank you.